Welcome to the course Formal Language and Automata Theory. In this lecture, we are going to discuss about equivalence between two finite state missions. It is denoted as FSM, also called as finite automatons. So till now we discussed about various topics related to finite automata, various types of finite automata, then regular expressions, then various forms of regular expressions, then converting regular expressions to automata, then automata to regular expressions. So various problems also discussed. So till now, we didn't focus about the equivalence of two automatons. So in this lecture, we will discuss about the equivalence between two finite state missions or finite automatons. Anything is same. So first we will discuss here. So what is equivalence? First of all, the definition. Finite state missions equivalence. Then there is one algorithm for showing the equivalence of automatons. So that is FSM equivalence algorithm. Then we will discuss about some example problems. Now let us see FSM equivalence. So how can we define or how can you say two finite automatons are equivalents or two finite state missions? So two FSMs, let us take M and M dash or two finite state missions are said to be equivalent if for each state Si. So Si is the state, suffix I means, so it may be a state 0, state 1 like that. So for each state Si of M, the first mission, there corresponds at least Sj of M dash, where Sj is the state corresponds to the second mission M dash. So whenever this corresponds exist, so where we will say Sj is equivalent to Si. Sj means the state of M dash mission is equivalent to the state of mission M. So that is Si. So then alternatively on for each Sj of M dash, the second mission M dash, so a state Sj, there corresponds at least one Si of M. So Si is the state of first mission M. So in this case, we will say Si is equivalent to Sj. Here you can see the order. So here we have mission M and mission M dash. So here we have considered Si is the state of M, then Sj is state of M dash. So first for mission M, for the state Si, there exists a corresponding state at least Sj of M dash. So in this case, we will call it as Sj is equivalent to Si. Whereas reverse, for Sj of M dash, second mission, there exists corresponding state Si of M. So then in this case, we will define Si is equivalent to Sj. So that is the definition of equivalence, FSM equivalence. So that means for first mission, for a state, there exists a corresponding state in the second mission. In this case, second mission state is equivalent to first mission state. Whereas for second mission state, there exists a corresponding state of first mission. So at that time, the order is Si is equivalent to Sj. Like that, we can define FSM equivalence. So now there is one algorithm to show the equivalence of two finite state missions or two finite automatons. So that algorithm is called as FSM equivalence algorithm, finite state missions equivalence algorithm. This algorithm was described by one of the famous scientists, E.F. Moore. So E.F. Moore has proposed an algorithm to determine whether or not two FSMs, let us say an A dash over an alphabet sigma or equivalent. So Moore proposed an algorithm to determine whether or not two finite state missions, let us say A and A dash, over an alphabet sigma are equivalent. This algorithm is based on checking the behavioral equivalence of two finite state missions by constructing a comparison table. So first, how to construct a comparison table? That is the first step of this equivalence algorithm. So Moore algorithm for checking the equivalence of two FSMs A and A dash over an alphabet sigma. So here we will consider mod sigma equal to n. So what is mod sigma? Number of input symbols in sigma. You can take the count of number of symbols in sigma. So let us say n. So now for simplicity, here we will consider sigma equal to 2 alphabets. So then n equal to mod sigma equal to 2. So where n is number of input symbols. So with this sigma value, now we can construct the comparison table. So step 1 of FSM equivalence algorithm so is construction of the comparison table. So how to construct comparison table? So in comparison table, here we will take n plus 1 columns. N plus 1 columns will be considered. Here we assumed n equal to mod sigma equal to 2. So that is equal to, so 2 plus 1 equal to 3 columns. So in comparison table, we will consider 3 columns. Now in column 1, what column 1 contains? List an ordered pair of vertices. Here vertices also called as states. So in transition diagram, all states are denoted by circle. So which is a directed graph. So in graph, nodes are vertices. So both will be the same. So now vertices are corresponds to states. So in column 1, list an ordered pair of vertices. So name it as V, then V dash, where V belongs to the first mission A and V dash belongs to the second mission A dash. So from first mission take one vertex, then the second mission take one vertex. Combination of these two vertices, so is called as a pair V comma V dash. So this can be listed in column 1 of the comparison table. Then coming to column 2, in column 2, list the pair of vertices. So V naught comma V naught dash. Here you can see our initial vertex pair is V comma V dash. Now we have taken V naught comma V naught dash. So when you can take this pair, if there is an arrow labeled 0, where 0 belongs to sigma, leading from V to V naught and V dash to V naught dash. Nothing but from vertex V on input 0, if there is a transition with on input 0, then going to another vertex or state V naught. So that is one pair. Then another one from V dash mission 2 with the input 0, it is going to V naught dash. So then you can take V naught dash. Now the pair becomes V naught comma V naught dash. So if V naught is the vertex of the mission A, then V naught dash is the vertex of mission A dash. So when this vertex will be considered whenever there is a transition from V on input 0, then the vertex name it as V naught. Then second one, so V dash on input 0, the vertex is V naught dash. So whenever there is a transition with input 0, then reaching to V naught or V naught dash, then you can take the pair as V naught comma V naught dash. That can be listed in column 2 of comparison table. Then coming to column 3, list the pair of vertices V1 comma V1 dash. Same. If there is an arrow labeled 1, 1 belongs to sigma leading from V2 V1 on input 1, then V dot dash 2 V1 dash on input 1. So now we have V on input 1, so the vertex is V1. Then from V dash on input 1, the vertex is V1 dash. Now we can take the pair as V1 comma V1 dash. That can be listed in column 3. Suppose if your sigma n equal to 3, let us assume. I mean mod sigma, 3 input symbols are there in sigma. Then your comparison table contains n plus 1, that is equal to 3 plus 1. So equal to 4 columns. So first column, you can take the vertex, initial vertex, v comma v dash. So then on first input, that can be listed in column 2, on second input that can be listed in column 3, then third input that can be listed in column 4. So n plus 1, 3 plus 1, 4 columns. Like that you can list. Now repeat this exercise for all other columns in the table. See the first one, if V0 comma V0 does not occur previously in column 1, then place it in column 1 of the next row and repeat the same process. We treat V1 V1 dash and the other pair similarly. This is nothing but here you can recall one of the conversion problem. So NFA to DFA conversion. So in this what we did, first we have taken initial state. So Q naught of NFA will be taken as the initial state of DFA. So is initial state of DFA. Then what we did later, so after finding transitions from the initial state on input 0, input 1, let us assume. So on input 0, if any new state occurred, that can be considered as the next state of DFA. Then on input 1, suppose if a new state occurred, that can be treated as the next state of DFA. So like that again for the next new states also we can find the transitions on the given inputs. Like that you can repeat until no new states are occurred, no changes are occurred. Here also same in column 1. So if any pair occurred in column 1 or 2, that is not already occurred in column 1. So at that time you can consider it as the next row of column 1. So then you can repeat the same process on input 0, on input 1. So like that. So like that you can build the comparison table for all combinations. Still no changes are occurred, no new pair occurred. So same as NFA to DFA, whatever the method 2 we followed. So that is step 1, construction of comparison table. Then coming to step 2, after construction of comparison table, by seeing the comparison table, we can establish the equivalence of two finite state machines. So the step 2 is establishment of the equivalence. So in comparison table, a pair V comma V dash is reached in which V is final state vertex of A and V dash is non-final state vertex of A dash. That is nothing but F comma NF or vice versa, NF comma F, where NF is non-final state, where F is final state. So whenever a pair exists with the combination of a final state of the first mission, comma a non-final state of second mission, or vice versa, means reverse, a non-final state of first mission, comma a final state of second mission. So any of these combination, both can't be exist. So any one is enough. So in this case, what you have to do, simply you have to stop. The FSMs are not equivalent. This is one conclusion. So whenever you will get in column 2 or column 3 of the comparison table, so if we have a pair combination of a final state, non-final state, or non-final state, final state combinations, simply at least one combination is enough with final state, non-final state, or non-final state, final state. So then you can stop, you can conclude the FSMs are not equivalent. Otherwise, suppose any of the above two cases not exist, Then you have to terminate when there are no new pairs in column 2, 3, and so on n that do not occur in column 1. You can find out all new pairs values from column 2 and 3. Those are all not occurred in column 1 till no new pairs are exist. Like NFA to DFA, when we have to stop. So whenever no new states are occurred, like that you have to continue. So in this case, we can say that two FSMs A and A dash are equivalent. So this is the conclusion. So you can recall once, this is very important. After construction of the comparison table, in comparison table column 2, 3, either 2 or 3, you can check any pair which is combination of a final state, non-final state, or non-final state, final state. Then we can stop, then we can conclude that two FSMs are not equivalent. Suppose we don't have any such combinations. So now we are getting the combinations like this. So what type of combinations you are getting? Both are final state combination or both are non-final state combination. So whenever these combinations exist, so you can find out all pairs values till no new pairs occurred in column 1. So then finally you can stop. The two FSMs are equivalent in this case. So this is the conclusion after constructing comparison table. Now let us see example problems. So the two problems we have considered here. So we will check in which case the FSMs are equal, then which case the FSMs are not equal. The question will be given like this. So in this also we may expect question in our examination. Check whether the two FSMs given below with sigma equal to 0, 1 are equivalent or not. The two finite automatons or finite state machines are given below figures. Here input alphabet sigma equal to 0, 1. See the following figures. Figure 1, finite state machine named as A. Then this is figure 2. So finite state machine named as A dash. Now both missions here you can see the inputs are combination of 0, 1. All the transitions you can see, which are combination of 0, 1. So now in the first mission, the states are named as 1, 2, 3. The second mission, the states are named as 1 dash, 2 dash, 3 dash, 4 dash. See the equivalence means generally many people think like same number of states in both missions, same transitions, same number of final states. So not like that. Whatever the equivalence algorithm described by E.F. Moore, we have to follow according to that algorithm. First, we have to construct comparison table. Then after construction of comparison table, the second step, establish the FSM equivalence by satisfying any of the two conditions. Like that, we have to check the equivalence of two finite state missions. So our first step is what you have to do. First, we have to construct comparison table. So in comparison table, as per the algorithm, so how many columns we have to take here? So here sigma equal to 0, 1 is given. So now you can take n equal to mod sigma, that is equal to sigma, how many inputs it contains? 2. So therefore 2. So therefore your comparison table contains n plus 1 equal to 2 plus 1 equal to 3 columns. So comparison table consisting of 3 columns here. So now see what column 1 contains, what column 2 contains, then what column 3 contains. So now you can see constructing comparison table. First we will consider n equal to mod sigma equal to 2 here. So therefore n plus 1 equal to 2 plus 1 equal to 3 columns in comparison table. So if sigma contains 3 alphabets, then here n equal to mod sigma equal to 3. So therefore 3 plus 1, so equal to 4 columns are exist in comparison table. Now in this case comparison table contains 3 columns. So now as per the first step, construction of comparison table, so what column 1 contains? So column 1 you can take the pair as v comma v dash, where V belongs to the first mission A and V dash belongs to the second mission A dash. So now the second column on the first input, here V naught dash. So here 0 is first input from sigma. So here sigma equal to 0 comma 1. So for the first input you can represent in column 2, that is V naught comma V naught dash. Then next column 3, the second input. The second input is 1. So here V1 comma V1 dash. So these you can make it as headings of comparison table. So now what you have to do, how to proceed? The first row. So that is row 1, what you have to do? You can take the initial states of both missions. So that is mission A and mission A dash. So what are the initial states? Those states you can consider in column 1 of first row. You can go back and check the two missions. Here you can see. So in the first mission A, 1 is the initial state. Why? Because prefixed with arrow. Then second mission, this is figure 2, A dash. Here 1 dash is the initial or start state. But here final states also same. But now we are considering only initial state pairs. So in the first mission, initial state is 1. The second mission, initial state is 1 dash. So this pair you can take initially in the first row of first column. Now you can see. So now we considered 1 comma 1 dash. Now in the second column, first row, you have to find out this value. How to find out? So here we have taken 1 comma 1 dash. Now see, on input 0, then on input 0 for both. See, from state 1 on input 0, what is its next state? Then from 1 dash on input 0, what is it next state? Again, you can take it these states as next pair. Now this can be written as so delta of 1 on 0 equal to, then this value is delta dash of 1 dash on 0. Find out this transition. So from state 1 on input 0, see, from state 1 on input 0, it is going back to 1 itself. So here you will get 1. From state 1 dash on 0, again it is going to 1 dash itself. So now here you will get the first transition, you will get 1. Here you will get 1 dash. Now the pair is so 1 comma 1 dash. So this will be included under V naught comma V naught dash. So this one. Similarly, 1 comma 1 dash on third column, that is input 1. So here this can be written as 1 comma 1 dash. So on input 1, this can be written as delta of 1 on 1. Then second mission, delta dash of 1 dash on input 1. So now here don't confuse 1 and so our state is also 1, then input is also 1, don't confuse. So in delta function, first one is state, second one is input. Now 1 on 1 from mission 1. From state 1 on input 1, it is going to state 2. So here you will get state 2. Then from mission A dash, from state 1 dash on input 1, it is going to 4 dash. So now here you will get 4 dash now. Now the pair is 2 comma 4 dash. This can be included in column 3 of row 1. Here you can see 2 comma 4 dash. So then as for our algorithm, whenever new pair is occurred, that can be considered in column 1 next row, you can consider it as the new pair. Now you can see 1 dash, this pair is same as this current one under column 1 pair, but you can see 2 comma 4 dash. 2 comma 4 dash is the new pair that can't be occurred previously in column 1. In column 1 initially we have taken only 1 comma 1 dash, but 2 comma 4 dash is the new pair that can't be occurred in column 1. So now you can include this pair as in column 1 of row 2. So this is row 2. Now we have to include 2 comma 4 dash. Repeat the same process used in row 1. So that is column 2 on input 0, then column 3 on input 1. You can find out the values. Now see 2 comma 4 dash on 0 input. That means from state 2 on input 0. So you will get state 3. Then from state 4 dash of mission, second mission, then on 0. So it is going to 2 dash. So again the pair is 3 comma 2 dash. Similarly on input 1, that is in column 3. So 2 on 1, from state 2 on input 1, it is going to state 1. Then state 4 dash 2 on input 1, it is going to 3 dash. So 1 comma 3 dash. Again you can see 3 comma 2 dash, 1 comma 3 dash are new pairs. So again these two you can consider as the next rows of column 1. So first let us take 3 comma 2 dash in row 3, then 1 comma 3 dash in row 4. So now again 3 comma 2 dash, repeat the same process. So 3 comma 2 dash on input 0, you will get 2 comma 1 dash. Then 3 comma 2 dash on input 1, you will get 3 comma 4 dash. Similarly 1 comma 3 dash on input 0, you will get 1 comma 2 dash. Then 1 comma 3 dash on input 1, you will get 2 comma 3 dash. Again you can see here 2 comma 1 dash is again new pair. 3 comma 4 dash is again new pair. Then 1 comma 2 dash. So you can check only column 1. If that pair already occurred, no need to take. If it is new, you can take. Now 1 comma 2 dash is also again new pair. 2 comma 3 dash is also new pair. So now again you can take 2 comma 1 dash, then 3 comma 4 dash. So then again you can find out their transitions. On 0, on 1, the new pairs are 3 comma 1 dash, 1 comma 4 dash. Now again 2 comma 2 dash, 3 comma 3 dash. Like that here you can see it is not stopping. So every time you are getting new pairs. So at that time actually you can stop. So whenever you are getting more repeated, I mean new pairs, if you are getting, you can stop there and you can check out in column 2 or 3 any pairs which are combination of final, non-final or non-final, final. Now you can see first column 2, 1 comma 1 dash. So here what are the final states now you can see. So here it is 1, here it is 1 dash. So now f equal to 1, now f dash equal to 1 dash. These are all the final states. So here we need to get a final of first mission or a non-final of second mission or a non-final state, final state of first mission or final state of second mission. If any such combinations are exist, let us check in column 2 and 3, 1 comma 1 dash. Here you can see both are final. This won't be considered. 2 comma 4 dash. Here both are non-final. Now 3 comma 2 dash, both are non-final. Now 1 comma 3 dash, here you can see 1 is final state of first mission, then 3 dash is non-final state of second mission. Now you can see the pair. So here the pair 1 comma 3 dash is in the form of final state comma non-final state. As per the theorem, step 2, establishing the equivalence of two FSMs. See the first case. F comma NF or NF comma F. Any one case exists, we have to stop. The FSMs are not equivalent. So even in the second row itself, so we obtained the combination final state comma non-final state. If any one combination exists, remaining no need to check. So now you can see the conclusion here. So here the pair 1 comma 3 dash in second row of third column, 1 comma 3 dash, where 1 belongs to final state of first mission, that is A, then 3 dash is non-final state of second mission. So therefore it is in the form of F comma NF. In the comparison table second row, so this is second row, then third column. Now this is third column. So now the pair is, the corresponding one is this one. So 1 comma 3 dash. So 1 comma 3 dash. Here 1 is final state of first mission A and 3 dash is non-final state of second mission A dash. So stop. The FSMs A and A dash are not equivalent. So whenever you will get any combination F comma NF or NF comma F, so we can stop, then the FSMs are not equivalent. So that conclusion is very important. Similarly, second example here you can see. So this you can practice. Here orally I will explain. Check whether the two FSMs given below sigma equal to C comma D are equivalent or not. Here the inputs are C comma D. Now the automatons are given in the form of transition table. So the M1 is given in the first table, then the M2 is given in the second table. The inputs are C comma D. So now the states are Q1, Q2, Q3 in mission 1. Then in mission 2, the states are continued Q4, Q5, Q6, Q7. Their transitions are given. So the step 1, what you have to do first, you can build the comparison table. So here sigma equal to contains two inputs C and D. Therefore, mod sigma equal to 2. Therefore, n plus 1, 2 plus 1, 3 columns are exist in the comparison table. So as usual, same as previous problem, first we can take V comma V dash in column 1. Then V on first input is C, that is V suffix C, and V dash on first input, that is C, V dash C in column 2, then column 3 on second input. So V on D, that is VD, then V dash on D. So V dash D. So that is in column 3. Here suffix C means first input, suffix D means second input. So now what you have to do, initially you can take the initial states of both missions. So here in the table, the initial state is included with prefix arrow. So in here M1 Q1 is the initial state and M2 Q4 is the initial state. Even final state also same, final state now not required. So now Q1, Q4 are the initial states of both missions. So you can take that pair in column 1 of row 1. So initial state of mission 1, that is Q1, then initial state of mission 2, that is Q4. Now same process, Q1 on input C. You can find out the transitions, then Q4 on input C from the second mission. So Q1 on C, it is going to Q1 itself. Then Q4 on C in the second mission, it is going to Q4. You can see the transition table and substitute. Now this is a pair. Then on input D, Q1 on input D, it is going to Q2. Then Q4 on input D in the second mission, it is going to Q5. Now you can see Q1, Q4, it is same as the current pair. But Q2, Q5, this is new pair. So Q2, Q5 is a new pair that you can include in column 1 of second row. So Q2, Q5. Now again Q2 on input C, you will get Q3. Then Q5 on input C, you will get Q6. Then Q2 on input D, you will get Q1. Then Q5 on input D, you will get Q4. So this Q4, Q1, Q4 already exist in column 1. So this is not new pair. But you can see Q3, Q6. So this is not occurred in column 1 of row 1, row 2. So this is new pair that you can consider as new pair in column 1 of row 3. Now Q3, Q6 is considered here. Again, you can repeat the same process. Q3 on C, you will get Q2. Q6 on C, you will get Q7. Then Q3 on D, you will get Q3. Q6 on D, you will get Q6. So now Q3, Q6, this is same as the current pair of column 1 of row 3. So, but Q2, Q7 not occurred in column 1 previously. So this you can consider as a new pair. This you can include next row, that is fourth row of column 1, that is Q2, Q7. Now Q2 on C, you will get Q3. Q7 on C, you will get Q6. Then Q2 on D, you will get Q1. Q7 on D, you will get Q4. See Q3, Q6, which is already occurred in the previous row of column 1. Then Q1, Q4 already occurred in the first row of column 1. See now no new pairs are occurred. So all pairs are repeated. So here now no new pairs exist. Now we can stop here. Now come back to our step 2 of equivalence algorithm. Establish the equivalence of two FSMs. Now see in the comparison table of column 2 and column 3. So this is column 2, this is column 3. All pairs are combination of. Here you can see either both are final states, that is F comma F, or both are non-final states, that is NF comma F. So and no new pairs are occurred in column 2 and 3 which are not included in column 1. Therefore, the two FSMs M1 and M2 are equivalent. Here you can see first let us check what are the final states in the given two missions. Q1, Q4 are the final states. Now in column 2, column 3 you can check. So here Q1, Q4 are the final states of both missions F comma F dash. Now you can see column 2, the pair Q1 comma Q4. See both are final comma final. Then Q2 comma Q5. So both are non-final. Then Q3 Q6 again both are non-final. Then Q1 Q4 both are final. Then Q2 Q7 non-final, again non-final. Then Q3 Q6 non-final, non-final. Q3 Q6 non-final, non-final. Q1 Q4 final, final. See, as for our algorithm case 1, so whenever you will get in column 2 or column 3 combination of a final, a non-final, or a non-final, final, then you can stop. Then you can say the FSMs are not equivalent. But here you can see all the combinations of the pairs in column 2, column 3, which are combination of both are final or both are non-final. That too, no new pairs are exist. So which are occurred in column 1. So that are already not included in column 1. So those can't be occurred in column 2 and 3. Therefore, the two FSMs M1 and M2 are equivalent. So in this case, the two FSMs are equal. In our first example, the two FSMs are not equivalent. Now we stop here. Now we will review the summary what we discussed. So first we discussed about what is FSM equivalence according to E.F. Moore. Then FSM equivalence algorithm, it has two steps. Step 1, comparison table construction. Step 2, establish equivalence of FSM equivalence. So according to this algorithm, we demonstrated two example problems. So example 1, FSMs are not equivalent, whereas example 2, FSMs are equal or equivalent. So these two examples are demonstrated. So next class we will come up with other interesting topics. Now we stop here.